Okay, this is chapter 4, lecture 4, and today we'll talk about molarity. Now, there are many ways to calculate and express concentration in chemistry. The most popular, the most often used, is molarity. Molarity is moles of solute per liter of solution, and we can express that big M equals N over L. And remember, it's liters of solution, total solution. Very often we will use brackets to represent molarity. So, for example, you can write that NaCl, sodium chloride, in brackets, equals 1.5 m. This would mean that the molarity of sodium chloride is 1.5 molar. And if we know the molarity then, and liters, then we can find moles. In other words, we can rearrange the equation. If we know liters, if we know molarity, we can rearrange and solve for moles, which then means we can solve for grams, for mass, because moles and mass are related through the periodic table. Okay, why don't we jump right in and try a problem. How many grams of solute are present in 50.0 milliliters of 1.33 molar potassium chloride? Let's go ahead and take our molarity equation. Molarity is moles over liters, and it looks like they're asking for grams, so we know we will be solving for moles, because moles and grams then are related through the periodic table. So first let's rearrange the equation so that we can solve for moles, and we'll do that by removing liters. Since liters is being divided, we'll go ahead and multiply by liters there, and we've got to do the same thing on this side to keep it equal. These cancel out. This is just algebraic manipulation, and we got ourselves moles equals liters times molarity. Simple as that. Now, because we're given milliliters, we'll have to convert from milliliters to liters. So it looks like we have 50.0 milliliters. Let's go ahead and convert that into liters. And milliliters will go down here. Liters on top. We know that a liter consists of 1,000 milliliters. And dividing by 1,000 will effectively just move the decimal place to the left 3 times. 1, 2, 3. And we end up with 0.0500 liters, keeping 3 significant figures here as in the original amount. Okay, let's go ahead and plug that into to solve for moles. Moles, therefore, equals 0.0500 multiplied by the molarity, which is 1.33. And if you compute that in a calculator, you should get yourself a fine value of 0.0665. So here's how many moles you got. They're asking us for grams, so we're going to have to convert that from moles to grams. And that's a simple mole to gram conversion, 0.0665 moles. Our substance is KCl. And so we'll have to pull from the periodic table the mass of KCl. We know that 1 mole goes in the bottom, and then grams of KCl goes on top. And so for KCl, looks like we got potassium, 3910, and chlorine should be 3545. For a total mass of, here's a 5, how about a 5, how about a 4, how about a 7, 74.55. This one ran away a little bit. Let's try again. 74.55 grams, so 74.55 grams. So we'll multiply that by our moles, 0.0665 times 74.55. And we get ourselves 4.96, rounding to 3 significant figures. This will be grams of KCl. Square that off as our final answer. So we'll require 4.96 grams of our solute for the solution. And we can do similar molarity problems solving for either the liters portion or the molarities portion. So be prepared for that. Okay, there are a few ways to prepare a solution. There are actually two major methods. The first is weighing and mixing a proper amount of solute and solvent, and this usually requires a solid. So anytime you have, say, you want to prepare a solution from a solid, this is typical of many salts, many bases, really most compounds you'll take from the back store, from a bottle, and that bottle will have a solid in it, some kind of potassium chloride or something, and then you have to weigh that out and literally dissolve it in some water. You can also take a concentrated solution and then dilute it, and this is true of many acids, because many acids do not come, in fact most acids do not come in a solid form. Acids are usually gases to begin with, dissolved in water, so you can order a very concentrated solution of an acid, and then you would end up diluting it. Hydrochloric acid, for example, comes stocked as a 12 molar. Sulfuric acid comes stocked as 18 molar, and then you take the stock bottle and you dilute it. So these are two separate methods depending on your application. So let's take a look at the first method. The question is, how do you make 500 milliliters of a half molar solution of barium chloride? So first, just like we did in the example problem, we find the number of moles. We rearrange the molarity equation like we've done and find the number of moles, which was, if you recall, liters times molarity. Then from moles you calculate grams, which we've done also, and then you would weigh it out and weigh out the solute, and then you would add solvent, which in most cases will be water, to the solute and mix. And here's kind of a picture of what you would do. So here we have weighed out our solute because it's a solid. Then we would throw it in this device. This is actually called a volumetric flask. This is a volumetric flask used for diluting. It's a little bit hard to see, but on the neck of this flask is a little mark that shows you exactly the volume. Usually these come in, this looks like probably a 500 milliliter flask. And on that neck would represent exactly this portion right here, 500 milliliters. So you would just dilute. First of all, usually you just mix a little bit of it and just pour a bunch of water in it, mix it as best you can, and then dilute to the little mark, which is around there. And just mix it up, and you got your solution. So this would be method one, preparing a dry substance, a solution from a dry substance. Method two would be begin with a known concentration, a very concentrated solution, and then diluting it. So diluting it means making it less concentrated. And in this case, what we would do, this one's a little more complex. We would find how many moles the second solution needs using molarity and volume, just using our molarity equation. And again, it's essentially the same equation. Moles is liters times molarity. And then using this amount of moles, you would find out how much volume the first solution you need using its molarity. So we're actually going to do a little example of this. There's a simpler way of doing it, and that's, here we have an equation that allows us to do exactly the same thing. This equation says that the initial molarity, this little I means initial, times initial volume gives you final molarity times final volume. And the reason this works, here it says, because the number of moles are the same in dilute and concentrated solutions. And because we've seen that moles is liters times molarity, or molarity times liters. Technically you've got yourself moles on this side and moles on this side, and the initial moles will be the same thing, the same as the final moles, because what we're taking an amount of moles from a concentrated solution and then transferring that same amount and then diluting it, so the moles stay the same is the idea. And here it says we can actually be in milliliters or liters, and that's because in the end your volumes will cancel out, and in the end you'll end up dividing the volumes by each other, and it doesn't matter whether they were milliliters or whether they were liters, they will actually cancel out. This is just a minor point. This doesn't make sense, don't worry too much about it. We'll make use of this equation here in a minute. And let's go ahead and finish with this example. And this example says how many milliliters of a 1.5 molar sodium hydroxide solution are needed to make 2 liters of 0.075 molar sodium hydroxide solution. So just thinking about this, what we're going to do is we'll do both methods, but looks like we have a concentrated solution. So here's our sodium hydroxide solution. We'll say this is our concentrated solution. It looks like this will be 1.5 molar. And essentially, what we need is we need to make a solution that's here's another beaker. Need to make a solution that's 0.075 molar. So the question is, how much do we take out of this solution and put in this solution? That's essentially what we're trying to find out. And then we'll simply fill it up to the 500 or to the 2 liter mark, 2.0 liter mark. That's the idea. We'll first find out, okay, how much do we need to take out of here? How many liters technically do we have to take out of here to make and then put in here? And how many liters will be found essentially from the moles. So what we'll do is we'll combine this information to get moles, and that will give us an equal amount of moles that we have to take out of this solution. So technically your moles would be the same. So I'm actually going to work it both ways, the long way, the logical way, and then we'll use that equation. Okay, so it looks like let's go ahead and find how many moles would be required for the new solution. So really, again, we've got ourselves moles. Well, molarity is moles over liters, so moles is liters times molarity in the second solution, which gives us moles equals 2.0 times 0.075. And 75 times 2 is about 150, so we got ourselves moles equals 0.150. This is how many moles we would need for the second solution. And now this is exactly how many moles we would need to take from the first solution. So now so this is the moles then we need to take out of the first solution. Well, we know that the first solution is 1.5 molar, so then we would have to take the equation again, the molarity equation, and rearrange it for liters, because we know the moles. The moles is right up here. We know the molarity, and let's rearrange for liters. In this case, what we'll do is we'll move liters over to this side by multiplying like we've done before, and we got ourselves liters times molarity is moles, and then we'll divide by molarity and put molarity on the other side. If you divide on this side, you've got to divide on the other side because of the equal sign, and you got yourself liters is moles over molarity. So let's go ahead and plug that in. Liters will equal, our moles is 0.150 divided by our molarity is 1.5. And effectively, we're just dividing by, we should get ourselves, if we double check this answer, 0.15 divided by 1.5 should get us 0.1. And 0.1, to use significant figures, 0.10 liters, which then if we convert to milliliters, we'll have to multiply by 1,000, multiply by, because a liter with dimensional analysis is 1,000 milliliters, so we get ourselves essentially 100 milliliters if you move the decimal 3 times over. So this essentially is our answer. And so what we could do then is we can use the other equation. The other equation said that the initial molarity times the initial volume equals the final molarity times the final volume. So essentially what we've got in this case is we've got ourselves the final molarity and final volume. Those numbers are right here. And we also know the initial molarity, so all we have to solve for is volume. So if we simply take and rearrange this equation to solve for volume, we'll end up dividing by dividing this by mi. You have to do it on both sides. And so our equation says Vi equals final molarity times final volume divided by initial molarity. So let's go and plug that in. Again, our final molarity is 0.075. That 7 looks a bit unpopular. There it is. And multiply that by our final volume, which in this case is 2. And then divide by our initial molarity, which in this case is 1.5. And what you'll see, essentially, we're doing exactly the same thing. In fact, if you take a look, we're multiplying these numbers exactly like we're doing here. And then that answer, which is here, gets divided by 1.5, which is exactly what we're doing. So this gives us exactly the same answer. We get 0.10 using single figures. And then liters, and then convert to milliliters again, you get yourself 100 milliliters of solution. And that should do it for lecture 4. Thanks so much.